Hello everyone, welcome to this video lecture for COMP3141. Having concluded our examination of monads and applicatives and functors, which is always a bit overwhelming for students, and I apologize for that, we're going to look a bit more at Haskell's type system and some of the ways that we can exploit Haskell's type system to ensure that our programs are safe and free of crash failures. So before I get into types, I just want to go over all of the different methods of assurance that we can use to ensure that our software is reliable. We have dynamic methods of software assurance, which include things like testing, and testing would be definitely the most common dynamic method of assurance, and it's what we've been doing most of in this course. All our property-based testing would fall under this area. But there are other methods of assurance that are commonly used as well. I would consider assert statements, such as those you find in C or Java, which would crash the program if a particular assumption is violated, is another dynamic method of assurance. And things like monitors and watchdogs, processes that monitor a running process and determine if it's doing anything wrong, like accessing invalid memory or committing security violations and things like that. All of those would be dynamic methods of assurance as well. So what these dynamic methods of assurance all have in common is that they all require us to run the program in order to determine if there is a fault. A static method, on the other hand, is a method of assurance that allows us to detect faults without running the program. So under static methods, we have the most common method being types, and we'll talk in this lecture about how we can use types to our advantage to ensure properties about our program. But we've already done this to a limited extent already in the course. For example, when we used new types to ensure that certain invariants were maintained. When we constructed a data type, our data invariants were maintained. We've done this stuff in general whenever we tried to avoid partial functions, and whenever we tried to make our types describe the situation as closely as possible. Our whole make illegal states unrepresentable mantra comes from this view of types as static assurance methods. Another static assurance method that we've used in this course is proofs. So you might think of proofs as perhaps dynamic in some sense because we sort of step through the evaluation of the program, but it's a symbolic evaluation that applies exhaustively to all possible executions of the program. So this pen and paper proof that we do, or a proof that is done in a machine-checked theorem prover, either way, both of them would be considered static methods of assurance because they don't require us to run the program. What we're doing is analyzing the program. Some of you may have used static analysis tools before. Many of them are commonly used to detect things like possible null pointer dereferencing or other possible failures. They can't be exhaustive in a Turing complete language, but what they can do is signal places where in your code where it's possible that an error might be present. And these static analyzers use a variety of techniques that we don't go into in this course, but there is another course, COMP3153, that I taught last term, which goes into these. And these static analyzers are widely used in industry, particularly I know I heard from John Carmack in the who works for founded id Software, who make games, that they use static analyzers all over the place to analyze their C++ code for memory safety problems. So these kinds of methods are also static methods of assurance, and pretty obviously because it's in the name. And another static method of assurance is a model checker. And a model checker is also covered in COMP3153, but essentially what they are a tool where you encode a model of your software. Usually it's not exactly the same thing as your program. It's a bit simpler in many ways. And it will automatically try and prove properties about it by exhaustively analyzing the entire state space of the program. And that's actually easier than it sounds. It depends on the properties, of course, and on the model as to whether or not it's feasible. But in any event, all of these methods do not require us to run the program per se. What they do require us to do is analyze it in some sense. And then we have methods that are both static and dynamic. So if you've used a language like Daphne, which many of you who are in software engineering might have in Senge 2011, I'm not sure about the code. But in any event, Daphne is a programming language where you can write assertions, like assert statements. But instead of those assert statements being checked at runtime, they are put through essentially a model checker, actually, to determine if they can be violated at compile time. So this is sort of a hybrid method where we define a contract, we define a preconditions and postconditions that we want our programs to satisfy, and it will combine dynamic checking and static checking in the one language. Another example of a combination of static and dynamic checking would be if any of you have used the language TypeScript, for example. It has what's called a gradual type system, which allows you to ascribe to some parts of your program some static types, and it will check those statically. And then other parts of your program can still have dynamic types. And then when you go from dynamic to static, it will require you to do some checking, some dynamic checking. So you have a combination of both untyped code in regular JavaScript, for example, in TypeScript, and then typed code, on the other hand, in the static area. And that would be the TypeScript code in the case of TypeScript. So we have this broad spectrum, really, of assurance methods. And so why should we prefer one over the other? Well, the big advantage of static checking is that static checks are exhaustive. And by that I mean it's able to analyze all possible executions of a program. If my type system says my function takes in an integer and returns a boolean, it does that in all cases, or at least all defined executions of that function. May not be fully defined, it may be partial, but it certainly will not return me a string. If I prove a property about my program, then that property holds for all cases that I proved it for. If my model checker comes back with a result, then that model checker's result applies to the model in all cases, because it exhaustively analyzed the state space. If a static checker says, this is definitely a mistake, you've definitely got a bug here, then it's right, assuming the static checker is sound. So all of these static methods that I've listed here are able to exhaustively analyze the entire space of possible executions of a program. But this is not in general possible for all programs and for all properties. Many of you who have done theoretical computer science courses, or even maybe in first year they might still teach it, I hope they do, you may have heard of the halting problem. And this halting problem says that it is in general not computable, i.e. it's not possible for any computer to decide if another program will halt in general. Another major problem, particularly in the area of model checking, is that some programs just have really, really large state spaces, and there's no way to realistically compact that state space to make it feasible to check in a reasonable amount of time. So we have so many states to check, and it's just impossible to check all of them. And so exhaustivity can require us to either sacrifice inexpressivity of our properties or give up on checking certain complicated programs. Dynamic checks, on the other hand, while they cannot be exhaustive, you can't exhaustively analyze all possible executions of the program, we do not have to make any sacrifices about the expressivity of our properties that we want to check, or the size or complexity of our program. So we can use dynamic methods whenever we do not have the ability or option of using a static method. Another important aspect about these methods of assurance is that most of them, even tests, which are very common, are not integrated into the compilation process. Why? What does that mean? Well, I can compile my program and run it, even deploy it to my users, with it still failing some tests, and this happens unfortunately often. I could change my program and my model checker's model might no longer reflect the reality of my program. If I write a proof about my program and then I change my program, then my program and my proof may not apply anymore to that program, and it may be useless anymore and may not show the property that I want. The only method of assurance that I have written here that is integrated into the compilation process is types. Whenever we run the compiler on our software, it checks the types for us. This is an extremely valuable property because they cannot diverge, they cannot differ from the source code itself. They are intrinsically tied to the source code because every time I put it through my compiler, it will check that for me. That means that my type signatures are impossible to diverge from the rest of the program. They are a machine-checked documentation, and they cannot be out of date. This also means that types are now the most widely used kind of formal verification. And they are a kind of formal verification because the compiler is doing the formal verification for us. And next week I'll be talking a bit about how type systems can be extended to encompass arbitrary proofs of arbitrary complexity. Turns out types are very powerful for this. And they're an exhaustive analysis. As we said before, it's impossible to write a program that obeys the type system in all but a couple of cases. It has to obey the type system in all cases. So, this week, what we're going to look at today is techniques to encode correctness conditions inside Haskell's type system. And we've done this a bit already, but I'm going to show you some new techniques that make this even more powerful. Okay. So, the first technique that I want to show you is called a phantom type. So, a phantom type is just, well, let's look at this example. I've got a new type here, it's just like a data type, called size, takes a parameter x, and it's equal to s of int. So the constructor is s, and the data contents is int. Now that's a bit strange. I've got this type parameter here, x, and it's not mentioned at all inside the definition of size. So this is called a phantom type parameter. So what's the point of having this? There's actually many very powerful use cases for this technique. We can use this parameter to track what data invariants have been established about a value. Essentially what it lets us do is introduce more type level distinctions than there are value level distinctions. So for example, if I have s of 7, I just know that that's a number 7. But then I can attach extra information on the type level to make 7 have some additional property. So for example, it could be that I've checked that this 7 was a valid input to my form, for example. Or I could check that I could attach this information to x that says this 7 is in meters, or it is in milliliters, or something like that. We could attach units of measure to our number, for example. Or we could enforce that certain things have to happen to this data before certain other things. We could enforce an ordering of the operations performed on a value. So these 3 use cases are the main use cases for phantom types, and I'll go through an example that demonstrates these 3 right now. So the first one we want to look at is data invariance, so specifically validation, right? So suppose I have a student ID data type, right? So internally, the student ID data type is just an integer. But students can be either undergraduates or postgraduates. So what I do, in order to encode that undergraduate or postgraduate information, I first add an extra parameter x to my student ID type, and then I define two empty data types, i.e. data types that have a type but no values associated with that type. So UG is just a type that's empty, and it's just used as a tag to fill in for this x parameter, right? So it's just introducing two type names that I'm going to use for x, and they're not actually going to be used as individual types by themselves. And then I'm going to define, instead of using this capital SID constructor here, I'm going to define my own smart constructor. So hopefully we remember from week 4 when we talked about smart constructors. Essentially what smart constructors do is they wrap around the normal type constructor, and they establish specific data invariants about that type constructor. So we have our smart constructor here called SID, all in lowercase, and it takes the integers just like the uppercase version, but instead of returning just a student ID x, it returns either, so left or right, a student ID undergraduate or a student ID postgraduate, depending on which one it is. We could even have a third option here if we really wanted to for I couldn't find that student number, but we're going to just crash in that case, I guess. It's not the most elegant, but it does ensure that the output is always a valid student ID. And then if we define functions like enroll in COMP3141, and it took in a student ID undergraduate to IO, then it's impossible for me to then pass in a student ID postgraduate to enroll in COMP3141, right? So if I only ever use this smart constructor, if I hide this regular constructor behind a module barrier or something, and I only ever use lowercase SID to construct these student ID types, then it would be impossible for me to pass in a postgraduate student to enroll in COMP3141. The type system would prevent it. However, if we did want to have a function that would work on either type of student, either undergraduate or postgraduate, we could still do that. We just call student ID x and use it for all possible x. Take in the student ID x and return IO string to look up their transcript, for example. Okay, so that's an example of using phantom types to encode data validation. So now we're going to look at using phantom types to encode units of measure. So if maybe most of you are too young to remember this. I'm only just old enough to remember it, so I guess that's true. I hope that most of you were born before this date, but actually that may not be true either. In 1999, there was some software on a Mars orbiter, that caused it to burn up on atmospheric entry because it confused units of force. It had some force measurement, and it assumed that it was in pounds, I believe, because it was written by American software developers, but it was actually in newtons because that's the standard measurement of force in physics. And this caused the Mars orbiter to do all sorts of wrong calculations, and it ended up coming into Earth's atmosphere at like a 90-degree angle and completely just burnt up. So we want to prevent that kind of loss of money and loss of scientific insight. And so what we will do is we'll have a value type, which is parameterized once again by this phantom type parameter x. And internally it's just an integer. But these two integers, U877 and U383, are tagged with a type level distinction that does not exist on the value level. in the type level, I've said that this value is in kilometers, and here this value is in miles. And once again, I've got two empty types to denote, this is like to denote the tags that I'm going to use for my values here. So what's the use of this? Well, this allows us, not only can we tell from the type system what unit a value is in, which is useful in itself, we can also impose constraints by carefully writing our types. So I've got a square A as another empty type here, but it takes a parameter. Area takes in two values and returns a square of those values. So for example, if I give it 2 kilometers values, then it will give me a value in square kilometers, right? Because it's the area of the two sides with the two sides rectangle. So the other interesting constraint that I have here is that the two units of the two inputs to area should be the same. So I can't give it one side in kilometers and one side in miles, because that would just not be a well-formed computation. So we can use phantom types to encode units of measure, and this is a common use case for them as well. Okay, a third case is the use of phantom types for enforcing ordering on operations. So if I have a socket, so it's like a network socket or something like that, and it has two possible states it can be in. It can be either in a state where it's ready to receive data, or a state where it's busy because it's sending data, let's say. Or let's just have an output-only socket, so it's ready to send or it's busy sending. So if the socket is busy, in order to send again, the user must first wait on the socket and block until the socket is ready. And then once the socket is ready, the user can send more data along the socket. And the thing that we don't want to have happen here is we don't want a user to send onto a socket and then send again before the socket is ready. So we have two states here. One is busy and one is ready. And our socket will be parameterized by an extra parameter s, which denotes the state it's in. Then the implementation of the socket isn't our concern at the moment. But our type signatures say wait requires a busy socket, and it will block and presumably only return once the socket is ready, and it will return a ready socket for us. And then if we send on the ready socket some string, presumably our data that we're sending, then we'll get back a busy socket. And in order to use that busy socket, we have to wait on it again, right? So this is enforcing that kind of wait, send ordering. But this is making one very key assumption that isn't necessarily guaranteed by Haskell's type system. So this assumption is essentially saying that when we send on a socket, a ready socket, we've got a ready socket, we pass it into send, we pass in our data to send, and then we get back the busy socket. Once we get back the busy socket, we'll never use the ready socket that we've put in to send again, right? We're assuming that we'll use these sockets in a linear way, and once I've used them once and passed them into this function, I'll never use them again. Similarly, once I use a busy socket, I'm never going to use it again. So here's a good example where I have sent on the socket with the value x, and then waited on the new socket, and then sent on the new socket with the value y, and gotten back the final socket, which is busy, and I return that one. This is sending 2 bits of data. But I could also just send on the initial ready socket my first bit of data, throw away the busy socket that I get back, and then send on the second socket, the second bit of data on the same ready socket that I sent the first one on, and then just return the busy socket from that. So here I've violated the invariant that we wanted, that we never send on a socket that we just sent from. So there are ways to solve this problem, but not in Haskell. There's a feature called linear type systems. The most famous example of a type system that is similar to this is the type system of Rust. So you can encode invariants like this using Rust's type system, but you can't do it quite yet in Haskell's type system, although there is work on an extension that may bring this kind of reasoning into Haskell as well. Yes. So I like these kinds of type systems because they were the topic of my doctoral research, but in general, these type systems are becoming more and more popular because people have realized their potential for managing stateful resources like this. But for now, we can't do this quite yet in Haskell, so while it is still nice to have this kind of interface, you would have to put in your documentation somewhere that you should never use stale values. And there is a few examples of this actually in Haskell's libraries. If you want really fast arrays, there's this library called vector, and inside that library it's got several cases where it's like, yes, please do not use old values if you pass them into this function or something like that. It's a little bit sad, but hopefully in the future we'll have a type system that's able to prevent that kind of thing. Okay, so the one other thing that's a bit ugly about these solutions, so we've seen all three use cases for phantom types now, but all three of these have made use of these extra type tags, right? Kilometers or miles, or UG and PG, or busy and ready, right? All of these extra type tags are of kind star, right? So we have, in our student ID example, student ID by itself, this word, is of kind star for the X to star, right? So it's star to star. Whereas so that means UG and PG are of kind star. But what else is of kind star? We have integers, they're of kind star. Booleans, they're of kind star. So that means I could say something like student ID string or student ID boolean. Well, that doesn't make sense. We only ever wanted the two possible tags to be UG and PG. So why is it okay for me to construct student ID of string? That doesn't make any sense. It's kind of unpleasant that our type system for our types is so untyped. I appreciate that sentence is a little complex, but what I'm saying is all of the kinds of our tags here is just star. If I had two different phantom types, ready and busy for my socket, for example, and UG and PG for my student ID, I could even have student ID of ready, even though that doesn't make any sense at all. The Haskell type system wouldn't complain. So what we want to do is narrow down the kind of X here so that instead of being just star, which is any old type, I want it to just be a kind that contains two possible kinds, two possible types you could guess, or two possible parameters here for X, UG and PG. They're the only possible values that I want to put in for my X parameter. So there's this feature in Haskell called data kinds, which allows us to do this. It's a language extension, which means that you have to put in an extra line on the top of your file, which describes what you're doing. So the two language extensions that we'll need is called data kinds and kind signatures. So kind signatures you will have already seen, which is just saying I want to be able to write a signature which tells Haskell compiler what kind my type is. But the data kinds extension allows us to use a data type as a kind instead of a type. So for example, I will define a data type here called stream, which is either undergraduate or postgraduate. And then using my kind signature, when I define the phantom type for student ID, I say that X is of kind stream. So I used a data type here as a kind. And that means that there's two possible types that I can have here, student ID of UG and student ID of PG. So because stream, the data type, was promoted up to the kind level, so now stream is a kind here, then UG and PG get promoted up to the type level. So they are now types of kind stream. Okay? But they're not types in the sense that they're types that have values. They're just things that are on the type level now. So what we've done is allowed ourselves to use these data types on the type level. And now if I define it this way, I can't define something like student ID string. That's not a well-formed thing to say. You can't just put any old type in there. You'd get a kind mismatch error. It would say, I expected something of kind stream, i.e. UG or PG, and you gave me a string, which is of kind star, right? So it's a kind mismatch. So this data type promotion feature cleans up the one sort of infelicity about these phantom types, which essentially is that they look a little bit hacky with these empty types that inhabit the kind star, but they're not even really types, they're just tags. Now we can have a separate kind for those tags and separate kinds for each one of the tags that we want to use. Okay, so that's phantom types. So now I'm going to do some programming, and this programming is going to be similar, very familiar for anyone who's done my course COMP3141. However, if you haven't done COMP3141, don't panic. I'm going to explain everything that I'm going to do. But essentially what we're going to be doing is writing a expression evaluator. So do I have a terminal? Doesn't look like I do. I'll just pull one up here. Let's clear that out. Okay, and now we write so we're going to have a data type which contains a syntax tree for an expression language. So we have Boolean constants, and I'll explain what a syntax tree is in a moment, don't worry. Essentially all this is doing is integer constants. All we're doing here is describing a series of expressions. And let's just make our expressions for Boolean and arithmetic computations. So I can define a Boolean as an expression, that's fine. I can have an integer constant as an expression, that's fine. I can have times of two expressions. I can compare two expressions to see one is less than the other. I can conjunct two expressions together, and I can do an if then else. So this is my little programming language. It's a very little one. And now I want to write a function that will evaluate this expression and return to me a value. Now a value, if we look at this syntax tree, it essentially is Boolean and arithmetic expressions. So it can either be a Boolean value that it returns, or it can be an integer value that it returns, right? So these are the two possibilities here. So now let's write our evaluator. The evaluator of a Boolean constant expression. So if I get a Boolean constant expression here to evaluate, I need to return a value. And the only value that really makes sense is bval, so I'll return the Boolean b inside bval. For integer constants, it's much the same story. Ival I. Now, for times, E1 and E2, well, what should I do here? I'm going to need to evaluate E1, right? And I'm also going to need to evaluate E2. And then I want to somehow combine those two results. So in order to do that, I need to know what eval E1 and eval E2 is going to return. If I just write V1 and then V2 and then I say, okay, return V1 times V2, that doesn't work. It's not going to be well typed because eval E1 returns a value and eval E2 returns a value. Not good. I don't know if that value is a Boolean or an integer. So what I need to do is say, well, I expect, because it's times, right, it's an arithmetic operation, the value I get back should be an integer. So I'll just pattern match in the let expression like this. So as eval E1 returns, it's going to match on ival V1. And then once I get my ival V1 and ival V2, I multiply V1 by V2 and return it in an ival as well, because times returns an integer. And then for less, well, I'm lazy, so I'm going to copy paste. So less is much the same story, except we return a bval because less obviously returns a Boolean return. And now for and, oops. We have two expressions here, and keeps happening. We expect these to be both Booleans. And we will return a Boolean and B2. And now for the final ingredient, we'll do if E1, E2. And in order to implement that, we just need to say, okay, well, I'm going to firstly evaluate E1. Oh, wait, sorry, there's a condition, a then, and an else. So I'm going to evaluate the condition, and it should be a Boolean. And then, depending on what that Boolean is, if it's true, then I'll return whatever ET is. Otherwise, I'll return whatever EE is. Okay, so there's my evaluator. So, if I save this and start up a stack REPL and load my expressions, then I can come up with an example. Let's try just something arbitrary. If times 2, no, I const 2, I const 3, let's go with less, I const 7, then b const true. I'm just trying to demonstrate all of the possible constructors here. No instance for show. We can fix that. Let's add one in. There we go. So we've got our expression there, and now if I try to evaluate it, oh, did I make a mistake? Oh no, I just forgot to put a $sign. I am very silly. There we go. Oh, and no instance for show either for this one. It's quickly fixed. Okay, and we can see that it's false. Is that correct? Let's check. 2 times 3 is 6. Is that less than 7? No. And oh, yes, of course, 6 is less than 7. What am I saying? And therefore it returns bconst false, which is what it returns. Excellent. So it does seem to evaluate correctly. Now let's try being a bit crafty here and introducing a problem. I'm going to say if and instead of less. right? I want to take the conjunction of these two numbers. Of course, that's not meaningful, that doesn't make sense. And if I try and evaluate it, it crashes. Non-exhaustive patterns in b-val b1. So that's a shame. What we have here is a partial function. And we all know what to do about partial functions. We need to either expand our codomain, i.e. usually with something like a maybe, and then we would have to, we could do it as a little example. It's similar to something I believe Curtis did in his previous lecture. But we could have this version where we return all of these, and then in the case of eval e1, we would just have to go case eval e1, eval e2 of, and then if both of these are, that's a bit annoying, we'd have to go do v1 is eval e1, v2 is eval e2, and then case v1, v2 of, and if they're both ivals, then we could go something like ival v1 prime times v2 prime, and we return that in pure. And then if it's anything else, i.e. something not well typed, we return nothing, right? So the maybe starts to come in there. And then you'd have to do very similar things for the other three cases. And this is quite unpleasant, I'm sure you'll agree. We can say less is like that. And then and is like that. And then if we first evaluate EC, and then if v1 case v1 of b-val true, then we eval et, b-val false, then we eval ee. And this is now our new version of our evaluator. We expanded our codomain using the maybe monad to eliminate the partiality, right? So now if I do this, it returns nothing, and if I do the correct one, it returns just of the correct answer. So that's better in the sense that we don't have any crashing program, but it's still not quite what we'd like. This code is now even longer than before, and it's even more annoying because we've got all of this annoying error checking, and all we really wanted to do was encode the same type checking that Haskell does on our expressions. So what we're going to try to do is, instead of doing this expanding the codomain, what we'll want to do is constrain the domain. That was the other technique, right? So instead of expanding the codomain to get rid of partiality, we'll try to constrain the domain so that eval is only going to be defined on well-typed expressions. And well-typed expressions will have a different type from non-well-typed expressions, or even non-well-typed expressions just won't be well-typed in Haskell at all. So what we're going to do is try to use our phantom type technique to do this, and we'll run into an obstacle here. It's not going to work completely, but we'll do our best. So we're going to first attach the phantom type, and now our expressions here need to take a parameter, and we can say, well, I expect the expression inside times to be an expression of type integer, and similarly here. and less as well also takes integer parameters. And as for and, well, we expect both of these to be booleans. So I'll change those. And then for if, well, I expect this one to be a boolean. The condition has to be a boolean. And then the other two, well, they can just be anything, right? They could be an integer, they could be a boolean, it doesn't matter. They just need to be the same. So I say it's any type t here. Okay. So this is my new definition for expressions. And for now, I will comment out this stuff, because as we change our expression type, it's probably going to break things here. But this was our old expression type. In fact, I'll also just put in the old expression type here so that I don't forget it later on when I'm putting the code up on the website. I don't want to have to retype it out. So I shouldn't delete anything that I write down. Pardon me while I do this. There we go. Okay, so that's all commented out now, so we don't need to worry about it. Okay, so now, as we said before, whenever we have our phantom type technique, what we're going to do is create some smart constructors. And what they're going to do is wrap around each of the constructors that we have here, and there'll be a more precise typed version of these constructors. Because if I just look at these constructors as they are right now, they're not quite precise enough. So if I look at the type of, say, times, it takes two integers as parameters, that sounds good, but then it returns expr of type t. It doesn't say that that t is also integer. We should expect that times takes an integer and another integer and returns an integer, but this type is just saying it takes an integer and returns and another integer and then returns anything you like. Could be an integer, could be anything else. So that's not quite what we want. And it's even more obvious if I show you another example. If I look at something like bconst, we'd expect that to be an expression of type boolean, but it in fact takes a boolean and is an expression of type t. So I could even have bconst of true is of type expression of type int, right? So we have a boolean here that is being given a expression of type int. So that's not good. We don't want to use these raw constructors. What we want to do instead is use our special smart constructors that associate to the type of these data a bit more information. So give us a bit more of a precise type. So my precise typed version of the bconst constructor will, like regular bconst with the capital B, take in a boolean and return an expression, but the return type is now going to say expression of type boolean. The body, though, is just going to be our regular constructor. Same with iconst. Take an integer, expression of type integer. Okay. Times, it takes in an expression of type integer, just like the regular times constructor, and another one. And this time, we can say the return type is of type integer as well. Less, expression of type integer, expression type integer, expression of type boolean this time, because less is a comparison operator. And then we have and, expression of type boolean, expression of type boolean, expression of type boolean. So the difference here between all of these constructors, these smart constructors, and the regular data constructors that we have here is that their return type isn't just expr t. Instead, we're specializing it to whichever return type we expect it to be. Now, if we look at the type of what we'd expect our if constructor to be, expr bool, expr t, and then we'd expect it to return, well, it's going to, if this condition is true, it's going to return this expr t, otherwise it'll be the second expr t. So either way, it returns expr t. But this is actually already, if I write if prime is undefined, this is already the type of our capital if. So for the capital if, we don't actually need a smart constructor for that one, and only for that one. The others all need a smart constructor to be precise enough. Okay, so that is our definitions. So now, if I go back to my editor and I want to so this is a correct expression. If I take this expression here and I change all of the constructors to my smart constructors, it should still work. It should still print out the expression. Yep. And if I look at the type though, it says it's an expert bool. Whereas if I look at the type of this expression with the regular constructors, it's of type expert T. So here we have more type information. And we can see that we have more because if I make that same type error and I change less to and, there's already something called and. I will fix that by hiding it. So the way you can hide things is by saying import hiding. So now it says, because I changed that less to and, it says I expected a expert bool because I have an and here, and you gave me an expert int, which is the times. So it's giving me a static type error instead of a runtime failure. So the Haskell won't even compile this invalid expression because I've used my smart constructors here. So if we were to define a module that exported only the constructor if and these smart constructors and none of these unsafe regular constructors here, bconst, iconst, times, less, and and, then we would have ourselves an interface where we could only construct well-typed expressions. And all of these non-well-typed expressions down here that we were crashing on would be impossible to construct. So that's good, right? So phantom types can really help us here. But there is a slight infelicity here. So I'll go back to the slides. I think these slides are just saying what we said before. Yeah. So if I take and of an integer and a boolean, that's not well typed, but it will accept it anyway. So we fixed that by either expanding the codomain, like we did with the maybe monad, or constraining it by restricting the type using phantom types, right? And we constructed all of these extra constructors, these smart constructors, for each of the operations. So this makes our bad expressions into type errors. If I take and of an integer and a boolean, couldn't match int and bool, right? Gives me a type error. So now, how should we write our evaluation function? Eval will take in an expression of type T, right? Evaluates any expression of type T. And when I evaluate an expression of type T, now I have more information than I had before. If I go back to my code, before, when I evaluated an expression of type T, I had to come back to some value, right? I'd return either a boolean or an integer, and I didn't know which one. But now, because the expression is of type T, I know which of the two types it's going to be. It's going to be T. So eval of expert T should return T, right? Whichever one it is. So let's try to implement our very first case. Let's do iconst. An integer constant is, well, if it's an iconst, then I expect this T should be int in this case. So I should be able to return I, right? Makes sense. So if that's the case, oh, no. GHC is saying, I'm not convinced that this T is int. Like, on what basis, GHC asks me, do I conclude that I is in fact, or that T is in fact an integer here? And I think, well, it's because I use the iconst constructor. But as we saw before, it's because it's not compiling, it's not going to run. So let me just do that. The type of iconst is not precise enough. So if I could even go iconst3 is of type, or bconst true is of type expert int, right? Or iconst3 is of type expert bool. So there's no enforced relationship in this constructor between the type that I expect it to be and the type that is actually there. The only reason we have that enforced is because we've used these smart constructors here. But GHC doesn't know that we've always used these smart constructors. It can't tell just by looking at the eval function that we constructed this expression using lowercase iconst. And it's not well formed in Haskell to use functions as patterns, so we can't say lowercase iconst here. It's a pattern. So we have to use a constructor, an actual data constructor. So the only data constructor we have is capital iconst, and that does not tell me the type information that I need. So somehow we need to educate GHC and tell GHC, actually, we are only ever going to construct iconst values that have expert int. And so when I pattern match on iconst, it will tell me that t is in fact integers, right? So if I tried to return I here, right now, it's just not convinced. So, yeah, we get this type error. So there is a solution to this, but it requires us to move a bit beyond phantom types. The phantom types technique is nice because it only requires basic Haskell. It's just adding an extra type parameter. But we're going to have to reach for another language extension in order to fix this problem. So this language extension is called Generalized Algebraic Data Types, or GADTs. Just have a drink of water. So GADTs, it's a fancy name for a fairly simple concept, although it's somewhat poorly explained, I think. So the first thing that GADTs let us do is express our data types a bit differently. So here I have a data type to express natural numbers. It's either 0 or it's the successor of another natural number. So for example, the number 3 is just successor of successor of successor of 0, right? So it's 0 plus 1 plus 1 plus 1, which is 3. It's a very inefficient way of describing natural numbers, but it's in fact the way that natural numbers are described in foundations of mathematics and in implementations of theorem provers and many other areas. So this is our definition of natural numbers, and it's just a regular Haskell data type, right? Data nat equals 0 as the first constructor, or the second constructor is s and it takes in a nat. That's straightforward, I hope. Now what GADTs let us do is say data nat is of kind star, right? So we introduce a kind signature here, where, and then you say z is a constructor that returns a nat. It takes no arguments and returns a nat. And s is a constructor that takes in a nat and returns a nat. So what we did here is actually just list out the types of the constructors for each of the constructors of our data type. So instead of writing it like a grammar, sort of like how you would write the values of the language of the data type, like in our normal data type declarations, here we just give each of the constructors a type like a functions type, except we don't provide a body because they're constructors, they're not actual implementations. So we can combine this data nat thing, or rather this GADT syntax where we describe the types of each of the constructors, with the type indexing trick that we just did with phantom types, right? So I'll show you on the code. Instead of writing it, pardon me, that's my calendar. Instead of writing our expressions, where's my mouse? There it is. Instead of writing our expressions like that, we're going to use the new GADT syntax. But in order to do that, I need to turn on my kind signatures. So I think for now I'll just need those two. Turn on my language extensions. So now I can define the same type as before. Expr T. Well, we know T is of kind star. Oops. And it takes in that star and returns a star. Right? Now that syntax might look a little bit confusing. Another way of writing this, and it's a bit clearer and it also works better in this case, is expr takes in something of kind star and returns something of kind star, right? Boolean or integer is our first parameter, and then we return at expr bool or expr int or whatever. So we first provide the kind signature, and then we provide each of the constructors. So bconst takes in a boolean, and the normal type of this would have been expr t, right? That's the type of the bconst up here. And similarly, iconst would have been int to expr t. But now, because we have to express on the right-hand side of the arrow here for each of the constructors, we have the return type of the constructor. In our previous example, our natural number type here was always the return type of all of the constructors, right? Because constructors construct the type that they are constructing. So our data type here, each of these constructors returns a nat. And here, each of these constructors are returning an expr. But because we didn't say expr t here, we just said expr and it's something of kind star to star, we can describe whichever return type we want for each of these constructors. So instead of saying expr t, which is what I'm forced to return in the normal syntax, I can instead return expr bool and make my type a bit more precise. And similarly, for iconst, I can return expr int. And you'll see it's actually just always going to be the types of our constructors, our smart constructors from before. So let's just use those. And we also need if. Can't forget that. So it takes in a boolean and an expr t and returns an expr t. So now that is our new version. And I just realized all of this code is actually on the slide, so I don't think I need to keep any of this. I think the only thing I didn't include was the actual evaluators, so I'll keep that separately. So now we have a new version of our data type. It looks similar to the old one, except we're now using the GADT syntax. And each of the constructors now has the completely precise type that describes both their input types and their output type in the type of the constructor itself. Now there's no distinction anymore between the smart constructor that we're supposed to use and the basic constructor that exists for the data type. So that means now when GHC sees that I've pattern matched on iconst I, it will see, well, iconst returns an expr int, so that tells me that the t here in expr t must be an integer. So it concludes from the pattern matching here, when I see iconst I, t must be an integer. Similarly, when I put in bconst b here, it will think, t is a boolean, and I can just return b. And then for times, e1, e2, well, this is an interesting thing. Previously, when we had our expanded codomain solution, we had to first evaluate E1 and then evaluate E2. So what I'm going to do here is evaluate E1. And because I know that E1 here is of type, according to the type of times, expr int, and E2 is also of type expr int, that means eval E1 and eval E2 is both going to be of type int, right? Because eval is of type expr t to t, and times is of type expr int to expr int to expr int. So E1 and E2 are both expr ints, so when I evaluate them, I get back an int. And then what I need to return is itself an int, because that's the return type of times, expr int. So I will just multiply eval E1 times eval E2. And the return types will line up. So one of the weird things that's happening here is this function is returning different types depending on the value that it's given as input. So this is what's called a dependent type, because what's happening here is I look at my value, the value that I get at input determines the type that I return as output. That's the very unusual thing about these type signatures. So next I'm going to look at my less expression, and it's much the same story. Here we're required to return a boolean, and my E1 and E2 are both integers. I can just do that. And same deal again. My laptop is making all sorts of noise right now. Eval E1, eval E2. And then we have if, the condition, the then, and the else. And here this is interesting. So we need to evaluate the condition, and then based on the condition we evaluate either ET or EE and return whatever it returns. So when we evaluate the condition, that's a boolean. So if the boolean is true, then I want to evaluate ET, else evaluate EE. And that's it. That's my evaluator. So this is a much more compact evaluator than this thing down here, which is almost a full screen. And it's way clearer what's going on, because on the left-hand side we have our expressions, and on the right-hand side we have Haskell code, and there's literally no errors that can possibly happen at runtime, which means all we do is literally just translate these expressions directly into the same typed Haskell code. Because the type systems of the expression language that we've defined here and Haskell's type system coincide, and we taught GHC that they do coincide. So when GHC sees that these expression is of type T, it will allow us to just return T. So with phantom types, we were able to construct an expression language that only has well-typed terms being constructible. And then with G80Ts, we were able to extend that to allow GHC to know that those two things are connected, that the type system of Haskell and the type system of the expression language is connected. And essentially what the difference between phantom types and G80Ts here is this pattern matching phenomena. With phantom types, when you pattern match, you don't learn any extra information about your type parameters. But with G80Ts, when you pattern match, you do learn some information about what your T, for example, is. It expands on the type parameters. Okay. Cool. Going back to the slides. So yeah, we have our code here. And now there's only one set of constructors. We don't have any smart constructors. And when I evaluate, I can just write the Haskell code that's equivalent to my expression. It's very nice. So this was the main motivating example for G80Ts when they were first introduced. But since they were introduced, people have discovered many, many other use cases for them. They turn out to be very useful. So I'm going to show you another example to get rid of another kind of partial function. So we could always write our own lists, right? We've written our own list types many times in this course so far, and this is hopefully one of the last times we'll do it. We have lists here. This is our own list type. It's just the same as our regular normal list type, except I've written it with G80T syntax. So what it says is list, it takes in a parameter of type a parameter A of kind star, and it returns a star. So in other words, it's of kind star to star here, but because I'm using a parameter here, not an index, I write it like this. And nil is our empty list, so it's just a constructor that returns a list of A without taking any parameters. And cons takes in an A and a tail, the list of A, and returns me my overall list with the two things put together. So we can define head and tail, which I've called here head and tail, because they are, otherwise they would alias the existing head and tail functions. And yeah, that's fine. They look they look good, but they are partial. So what we want to do is constrain the domain of these functions by tracking the length of them on the type level. So let's go to the code to do that. So firstly, I'm just going to write down this list implementation. List a star where nil list of a cons takes an a and a list of a and a list of a, and our head cons x's is x and a tail cons x's is x's, right? Okay, so now what we want to do is track these lengths on the type level. So in order to track a length, we'll first need to define a data type that encodes the length. And while numbers do exist on the type level in Haskell, that feature is still quite experimental. So I'm just going to define a data type and promote it to the type level using data kinds, right? So we've seen data kinds before, and I'm going to use them again here. Data nat takes in a 0, is either 0 or its successor of nat. I'm just using a regular data type syntax here. I don't have to use GADTs for this one. And now, in order to make my list into a vector, this is typically what they're called. When we track the length on the type level, for some reason they decided to call them vectors. Don't ask me why. It's not my decision. And the extra parameter here that I'm going to give it is an index that I'm going to call nat, right? It's of kind nat because I'm tracking the length on the type level. So the extra parameter here for nil is going to be length 0. And then here, if my tail is of length n, then my length of the vector here will be successor of n, right? So let's do some examples here. Doesn't like that. Did I do something wrong? I think it just doesn't like that I wrote a type signature here. Let's just write something very wrong here for now, and we'll fix it later. Have to write the correct one here, or otherwise it will still complain. I wrote an error here as well. I should have written expertise. Okay, now I can actually, I should go back and evaluate this example just to double check that it is still working. So now if I take my correct, oh, that was the incorrect one. If I change my and back to less, it evaluates to false. And note it doesn't evaluate to be val false, it just evaluates to false. So cool, that works. So now moving on to our lists, if I construct, right, if I construct cons of 3, cons of 4 nil, I can't print it right now because I didn't derive show. So how do we derive show when we have GADTs? Well, we can't normally. But if I turn on a special language extension called standalone deriving, this line is getting very long, then I can write deriving instance of show for vec a n, assuming that there is an instance of show for a. Right, so this is just like writing an ordinary instance declaration, except instead of writing where and then providing implementations, you just put the word deriving beforehand, and it will derive the instance automatically when it can. And it will do that here for our vectors. Okay. And so now, if I look at this list, it seems to look fine. And the type, though, says vector A of successor of 0. And this apostrophe just means it's a data constructor that's been promoted to the type level. So we have vector here of length 2. That's 2, right? And if I add another element, then it's one more attached to the type. So now, actually, I can even take the head of this there we go. Head of cons 3, cons 4, cons 5 is 3. Seems good. But then if I go head of nil, it still will crash, right? It's because we didn't make the type specific enough. Here I said this will take a vector of any length, of any type A and any length n. But I want the length to be any length bigger than or equal to 1. So I say it's got to be the successor of something. It can't be nil. Nil is the only thing which is vec AZ. Everything else is successor of something. So I expect it to be cons. So I will say that the length has to be the successor of something. Has to be n plus 1. And that's what I did in tail here as well. And now if I try and take the head of nil, it's a type error. It's not a runtime error. Similarly, but I can still take the head of a non-empty list. And similarly for tail, if I do that, or tail of nil, there we go. Okay, so I've used quite a few different type level features here. I first used data kinds to promote these natural numbers to the type level and used them with my kind signature here when I attached it to this GADT, which defines the vector, and I derived show using standalone deriving, right? So these are quite a few extensions here, but they all pretty well behaved with each other. Okay, back to the slides. So we defined the natural number, defined our vector, and now we can make these total functions. Oops, I will actually code this live. I think it would be nice. So now let's define another function, map, for vectors. So it's like map for lists. It's just going to take a function a to b and take a vector of a's and give me a vector of b's. But the vector is of length n, and we know that our output should be the same length if it's a law-abiding map implementation. So vec bn will say that the length has to be the same. So now if I write my function, well, it's just like ordinary map. If I have cons x x's, then it's cons of f of x map vec f x's. Easy. And if I run that through my compiler, it says fine. So one of the coolest things here, and we can just double check that it works by writing a quick example, macvec plus 1, there we go. Does work indeed. So the cool thing here is that the compiler has automatically verified that I have returned a list of the same length as my input. So if I did something wrong, like forget to do the cons part here, it would give me an error and say, no, it's got to be the same length. And we didn't do something of the same length here. We're just returning the empty list. So we have automatically, formally even, verified that the length of the output is the same as the length of the input. And the compiler is automatically checking this formal property for us. So that's very nice. And now it's almost impossible. It is theoretically possible, but it's very, very hard. You'd have to try very hard to write a version of this map function that disobeys the functor laws. It's almost, there's only one thing you can do that would break the functor laws here. Maybe if anyone can think of it, post it in the piazza. It might be a nice exercise. Okay. So there's our map function. And we've just used it to formally verify a property using the compiler's type system, right? So we've proven for all cases that the length of the output of map is the same as the length of the input without having to do anything, right? All we did was give it a more precise type. So this kind of checking is obviously beneficial in that we were able to verify properties without having to test them or prove them. But, you know, it comes with trade-offs. it can be difficult to convince the Haskell type checker that our code actually is correct, even though it is. Sometimes Haskell's type solver isn't that smart, and you have to beat it around a bit in order to get it to understand. And we'll see some examples of that in a moment. As you've seen, the syntax starts to get a bit complicated. We've got kinds and types and all of this stuff going on. It's a bit more complicated than standard Haskell, which can make it a bit harder to understand. It's a bit more verbose. If you have all of this type level stuff, it can get confusing for newcomers to Haskell. And sometimes, if you have excessively detailed types, it can make the GHC type checker very slow, although this is a lot better in recent versions, which, if you have slow compile times, that can hinder your productivity. And this isn't just the case in Haskell. Type-level programming is also very popular in languages like C++, and in C++ in particular, type-level programming can introduce severe compile time delays. So we need to be pragmatic about this. We should judiciously use these type-level checks when the assurance advantages outweigh the clarity disadvantages. So the main use case for doing this is to eliminate partial functions, right? Because that's always the danger zone when we're looking for bugs. So if we can eliminate partial functions, it's probably a good idea to give it a go. But if you never use a partial list function, for example, then having a length index vector doesn't help you at all. So you've got to be careful about what information you actually want to track on the type level. If you never care about how large a piece of data is, then it doesn't serve you to track that information in the type level. You only need to care if you need to make the distinction in order to avoid a crash or avoid a failure. Okay, so the last thing I want to talk about is one more feature of Haskell's type system that becomes very useful once we have these GADTs and so on. Suppose I wanted to append two vectors together. I have my vector of a's of length m and my vector of a's of length n, and I want to append them together, so it's just the plus plus operator, but it's written as append here for our vectors. If I wanted to append them, I would expect that the output size would be the sum of the two inputs, right? So going to my code, where's my code? Here we go. I would expect to be able to write something like this. Vec am, vec an, vec m plus n. But I can't actually write this because of two reasons. One, plus is not defined on my nat type. It's only defined on like ints and floats and so on. So can't use plus. But if I define my own plus, let's do that actually for educational purposes. If I define plus of 0 and n, that's n. If I define plus of successor of m and n, that's successor of plus m and n, right? So we just move the successors out and you end up with the addition. And this is how addition is defined in formal theories of mathematics. Okay, so now if I want to define append, I could try writing like this. But according to Haskell, this would mean I have a type variable called plus, and it wouldn't think that I'm using the value level function on the type level here. In fact, we can't just take a value level function and apply it to type level values. So because I'm using these natural numbers on the type level rather than on the value level, I can't just take this value level function and put it in here. So the feature that Haskell introduces to solve this problem is essentially type level functions, right? So we want to write m plus n, but we do not have addition defined for the kind, not type, kind nat, right? We could define this normal Haskell function, we just did, but it's not applicable to the type level natural numbers. So to get a type level function, we use an extra extension, which is called type families. And that essentially means type functions. They are a bit more general than functions. They allow you to do more things than just having type level functions, but all we're going to use them for is type level functions. So the way you write it is, I have a type family, and my Vim syntax highlighting is out of date, so it doesn't think family is a keyword, but it is. And it takes in, it's called plus, right? And because it's on the type level, it's got a capital letter, not a lowercase one. It takes in a natural number, x, and a natural number, y. And its ultimate return kind is nat, right? So these are all kinds, x, y, and the return. Plus, and the body is almost exactly the same, except we use capital P because it's type level. Right, but otherwise it's identical to the lowercase plus that we used on the value level. And now with that type family, I can define append. I just write it like this. Append takes in my vectors. If the left-hand vector is nil, then I just return the right-hand vector. If the left-hand vector is cons, x-axis, and the right-hand vector there, then I append, I put cons in front, and then I append the rest of the left-hand vector with the right-hand vector. So now, if I do this, yep, GHC checks that fine, and I can even take my example here. Let's call this V, and then append V to V, and I get, let's do get a nice big one. We could even ask how big is this, and it will say it's that big, however big that is. If I even partially apply append V, I ask what's the type of that, it will say, it will give me, take a vector of length n and give me a vector of length n plus 3, right? Because the length of V is 3, right? So we can see that it's doing this length tracking quite elegantly without us having to specify anything about what's going on. So that's nice. But now I'm going to show you a way where Haskells can get very confused. Suppose that instead of writing m plus n, I wrote n plus m. Now we know, as humans who are familiar with arithmetic, that n plus m and m plus n are the same, right? It's commutative. But you're probably guessing that Haskell does not realize that, and you would be right. So if I do it this way, it gives me all these sorts of things. It says, I couldn't figure out that n plus 0 is n. This squiggly line means equals. So it says, I couldn't figure out that these two things were equal. And it's saying, couldn't figure out that n plus 0 is n. But we know that's true. I couldn't figure out that n plus successor of n1 is equal to successor of n plus n1. But that's also true. So how do we get around this problem? Well, see, we know how to get around it these days. We could just flip this and this. But the reason this problem happened in the first place was that the structure of plus, my type family here, and the structure of append no longer match up. When I have it written as mn rather than nm, then the left hand, if we look at plus here, it's recursing on the left hand side, and when it's at 0, it returns the thing on the right hand side, and then when it's a successor, it takes successor of the combination of the x and y. And here, when it's nil, it returns the thing on the right-hand side, similar to the 0 case. And when it's cons, similar to the successor case, it returns the cons of the combination of the x and y, right? It's the same thing as this structure. And because these structures line up, that's why Haskell can tell that this is in fact returning the same, the length plus mn. If I did it this way, I would have to flip around the definition of plus, and I can do that. I'll show you. if I did it around the other way, like that, then it should work. And indeed it does, right? Because I flipped around how plus is structured. But the structure has to line up. Now I'm going to flip that around again because otherwise it's going to be a little weird to have them flipped in the opposite order to the append function. So I'm just going to undo those changes I just made. But it was just a demonstration. Okay. So now I think we're back to normal. Yeah. So one of the cool things here is, let's just scroll back up again. The append function here has also been verified to satisfy a certain property, that the m and n will be the, like if we add up m and n, we'll get the length of the appended list, right? So we have that property also automatically verified for us, which is very nice. So we have to be careful when we define these type families to make sure that the structure of the type family, in terms of the recursive cases and where you put your constructors, matches in some sense the places where you'd put the constructors on the implementation that uses it. And you'll encounter some more examples of this as we go along. Okay. Cool. So yeah, this is just pointing out the same problem. Now, in order to address this problem, another way we could have approached it is we could have said, well, no, it's not good enough that Haskell doesn't realize that plus is commutative. Maybe I can just prove to Haskell that plus is commutative, and then everything will be fine. And there is a way to do this. I won't talk about it today, but in week 10, I'm going to do an extension lecture on using types as proof systems, and there I will show you a way to prove properties about addition and so on in the type level. But that's in week 10, and it won't be examined. Right. Okay, cool. So this is only a very lightweight taste of the full power of using types to enforce your specifications. So languages with better support for dependent types, specifically the two languages I like best are Idris and Agda, and I encourage you to learn these two languages, completely merge the type and value level languages. So instead of having type families and value level functions, I could have just used my value level plus function on the type level. And in fact, that's just very natural and very easy to do in those languages. They completely combine the type and value level languages, which means that we can encode arbitrary properties in our types, and it's very natural to move things from the type to the value level and back. Haskell is getting more and more of these features all the time. There's a research program called Dependent Haskell, which is trying to introduce these features into Haskell. And there's problems in integrating this into an already existing language, which is why we still have some sort of infelicities about this, and why it's still not quite perfect, and we still have a few technical problems with it. But next week I'm going to be talking a bit more theoretically than most of this course had so far, because types turn out to actually be a very fundamental part of computer science. You might have thought that they were just sanity checking features of your programming language, but in fact type systems are as foundational to our reasoning as logic is and proofs are. In fact, we have a mathematical result that says that types are the same thing as logical propositions, and programs that inhabit those types are the same thing as proofs of those propositions. And I'll be talking about that. I'll also be talking about how we can exploit the fact that types are all made up of the same sort of fundamental building blocks to generate algorithms on arbitrary data structures without even knowing what those data structures are. And this is actually how Haskell does its deriving methodology. And then the last thing I'll talk about is a property called parametricity, which I made reference to very early on in the course when we talked about functor. Because when we talked about functor, I said something that may have confused some of you. I said that if a program satisfies the first functor law, fmap of ID is ID, then the second functor law is already satisfied. It's impossible to write a program that satisfies the first functor law and violates the second. And that seems a bit surprising and it's a bit strange because the second functor law looks harder to satisfy. It's about composition. But this is actually a consequence of the polymorphism in Haskell's type system. And I'll be talking about that next week as well. So the last thing I want to mention today is that assignment 2 is released, and I just realized that that type signature, that time is incorrect. I forgot to update it. I will show you on the course website so that you do not, please disregard that time. I'm just going to scroll away from it before you look at it too long. And I'm just going to grab the spec here and I'll talk about it a bit. Okay, so here's the spec. And it's due on the 5th of August. I think that sounds more accurate. It says 2020, so I'm going to believe that. And this explains the pixel art that's on the course website. So here we're implementing a regular expressions engine. I hope many of you have seen regular expressions already, either in your editors or in COMP3141 or wherever. And if you haven't seen them before, essentially what they are is an expression language that lets you describe patterns of text. So we have empty, which is describing the empty string, fail, which describes no strings, characters, which describes a single character from a sequence of characters that we provide in this list. And then you can put two regular expressions together next to each other, and then it will have to be the first regular expression followed by whatever is matched by the second regular expression. We can choose between two, so it's either the first or the second, or we can have 0 or more times of the given regular expression. That's what star is. So some examples here. If I have the characters 0 through 9, so it will be one of these characters, 0 through to 9, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 or more times, so 0 or more digits here, followed by one more digit. So in other words, this is one or more digits. So that's some examples of strings that it would match. And then we have here, choose between 0 or more A's or 0 or more B's. So it's empty string or A or B or AA or BB, but you can't have like AB or anything like that. Fail is just nothing. Empty is the empty string, right? So in order to implement this, you have to use a monad, right? We have this monad here called hair. And unlike the monads that you've used so far, it is parameterized by another monad, right? So internally, although you will not have to look inside the implementation of hair very often, it takes in a string, which is the string it's matching, and returns an f, which is whichever monad is passed in as the parameter of string in A. So it's, in other words, it's adding this state, this string state, to whatever monad you already are using. So why do we have this extra monad parameter? Well, there's two main monads that we want to use with hair. One is maybe, and if we use maybe, then it will only find the first match of a particular irregular expression in the given text. And if you use list, then it will find all possible matches of the given regular expression. And the assignment gives you some tutorial here about how to do that, basically. Now, the other complication of this assignment is that we are not just using this basic regular expression type. This is not well typed enough for us. We want to have a more richly typed regular expression language. So we're going to use a GADT to describe that regular expression language. and we made a start for you, but we didn't finish the implementation of it. So in order to do the typed regular expression, you'll have to define all of the constructors of the regular expression language with more accurate types. Okay? And then you'll need to implement the matching algorithm, which we've already provided to you using the hair monad. So we actually already provided the matching algorithm, except that it uses the untyped representation with this special results type, right? We get rid of the results type in the typed version. So in order to understand how to use the monad and how to use this alternative type class and so on, you can look at this code, which we already have for the untyped matching code. And then when you adapt it to the typed version, which you'll implement by adding those extra constructors, then you just need to change bits and pieces of it, and most of the monadic code stays the same. So yes, you're using a complicated monad, but it's not a very difficult use of the complicated monad. Once you've implemented the match implementation and you've gotten your constructors added, you'll also then have to implement a few extra combinators that make things a little bit easier. You add this extra constructor here, which looks a little bit like fmap, and then you need to implement a few utility functions, one to help you construct lists, one to take one or more as opposed to 0 or more, and one to match on a particular string like COMP3141, so it's the letter C followed by the letter O followed by the letter M and so on. Choose, which lets you choose between 0 or more options rather than just 2, and option, which lets you make something optional using returning a maybe, and repeat, which lets you repeat a particular regular expression n times, right? So, and repeat range and a few other bits. So there's a few combinators here that you have to implement, and once you've done that, so you implement your type version, you implement match, you implement all your combinators, that's it. That's the assignment. And you can test this assignment on a anonymized, partially, UNSW transcript that I have provided as a test case, but you can also write your own tests, and we have some extra tests that we're keeping to ourselves. Yes, if you can de-anonymize the transcript, feel free to go ahead and try. You won't find anything of particularly private or sensitive information there, so don't worry about that. Okay, you can test this much like you tested Tortoise. So I think everything is set up pretty much the same way. So make sure you get started on it soon, have a think about it, make sure you know what you're doing within a few days so that you can at least make a start. The main challenge here is that you won't be able to test anything until after you've implemented all of the constructors, right? So you first have to add all of those typed constructors and get the types right, or otherwise nothing will compile. And if nothing compiles, nothing can be run, nothing can be tested, no marks can be gotten. So you do need to make sure you get all those types in there. And once you've done that, you can do everything else. Okay. Cool. That's all I have to say to there. Ignore that time. I'm just going to go back so that it's gone. There's also a quiz up as usual, and I'll see you next week for an interesting look at type theory. Thank you very much.